Hi, my name is Scarlett Simmon, and I'm going to go through Physics Lab 3, the black hole. So here's what I'm going to talk about today. First of all, the purpose of this experiment was to find the mass of a black hole with a computational model that analyzes the star's orbit. And then I used these calculations to find the initial velocity of a ship, leaving a planet orbiting the planet and the black hole that allows it not to crash. And the main result is that I found that the mass of the black hole was 1.84 to the 10 to the 34th kilograms, and this was my initial velocity, and I'll go into how I got that. So here's some fundamental principles. Newton's second law, F net equals dp dt. F net parallel and F net perpendicular were really important in this. Velocity update and position update, which I used in my code. Newton's universal law of gravitation and the magnitude were all super important. Here are my assumptions. So I assume that F net equals Fg because the only force acting on the system is the force of gravity, and dp dt equals gmm over r squared. So for finding the mass, my system was the black hole, my surroundings were the star. Some initial conditions: mass of the star, 2 times 10 to the 30th, which we were given, starting time 0, and then delta T is seconds in an Earth day, and then the gravitational constant. So what changed in the code? First, I applied Newton's second law to the code, and this allowed me to find the mass of the black hole. And then this is what I found out. Here is my code. If it will open. Yeah. So this is my code, and then when I run the program, this is what it looks like, and this helped me find the mass of the black hole because I averaged all of the numbers below. And then for finding the velocity of the spaceship, the system was the spaceship and the surroundings were the black hole and the planet. Here are my initial conditions on the right, and then some other things that I updated, like I put in the black hole mass, and then my initial conditions for the spaceship, my ship speed, x and y. And then to calculate the net force and to find the velocity, I had to update the code to get the net force on the planet and the net force on the ship so that the ship was impacted by both. So you can see here how I did that code. And then for applying Newton's second law, I had the velocity update and the position update, which again you can see on the right. The parentheses in Python really help with like making sure that it understands what is being divided and multiplied, so I use those a lot. And then with the trial and error, I found the initial velocity of the ship could have been 20,000 and 38,000. This was trial and error, and I'll go into a little bit of that later, but this is my code. And then when I run the program, you can see it's kind of a weird orbit, but I know that the orbit is being affected by both the planet and the moon because the orbit changes. And if it were just the moon, then the orbit would be the same the whole time because the moon is moving, but the planet is not. And then some possible errors. First of all, I assume there are no other outside forces, which in real life there could be. And then this is a simulation, so it's not guaranteed to accurately represent reality. The mass of the black hole could be off because black holes can vary in size. And then for part 2, I used trial and error to find initial velocity, so there could be a better velocity vector to better model a figure 8 orbit. Obviously, I didn't get a figure 8 orbit, so I could definitely have improved that. And then what does it mean? How is the net force different from rate of change of momentum? Mathematically, they're the same, but you can find them in 2 different ways. And the rate of changes of momentum is easier to find because you only need change in velocity over time, whereas with the net force, you need all of the forces acting on the system, which can sometimes be a little difficult to find. And then what if? To predict the motion of the entire system, everything would have to be included in the system, meaning nothing would be in the surroundings. This allows for kinetic energy and gravitational potential energy in the energy conservation equation. And then for some reason my slide didn't update, but the most dominant force would be the one with the greatest mass because of the nature of both kinetic energy and gravitational potential energy. And that is all. Thank you.